Right, continuing, and this is part of the work dealing with triangles again, and something called the sine rule. Up until this moment in time, if you had a triangle and I asked you to work out an angle in a triangle, or the length of a side of a triangle, you could perhaps use Pythagoras for the length of a side, or SOHCAHTOA for the size of an angle, or the length of a side. But one thing was certainly true, the triangle had to be right angled for Pythagoras or SOHCAHTOA. So we've got another couple of rules, sine rule and next day's work, cosine rule, which work for any triangle, non-right angle triangles as well as right angle triangles. Okay, so here it is, there's the sine rule. Same notation as the area of triangle. Our angles are capitals A, B and C and lowercase for the sides A, B and C. And you can see the sine rule. It's just a ratio. A over sine A is equal to B over sine B is equal to C over sine C. It's quite easy to use, as you'll see in the next screen when we look at an example. Okay, so what we've got in this triangle is I've got two angles and a side, and I'm asking you to find the length of BC. Well, there is BC, and because it's across from angle A, I've called it small a. So first things first, I would quite simply state the sine rule for this one. So I would say using sine rule, you're just basically telling the examiner you know what you're doing. So it's A over sine A is equal to B over sine B is equal to C over sine C. What now? Let's go through this. What are we trying to find? We're trying to find the length of BC. We're trying to find the length of small a, in other words. So that's the one I'm trying to find. So I'm going to put a wee question mark here. Do I know capital A? Do I know angle A? Yes, I do. So I'm going to put a tick beside the ones I do know. Do I know the length of side B? Small b? No, so I'm putting a cross. Do I know the size of angle B? Well, I could work it out, right, because I've got these two, so I could work that one out. So I could put a tick there. And do I know small c? Yes, it's 8. And do I know the angle at C? Yes, it's 54. Now, we've got three ratios there, A over sine A, B over sine B, C over sine C, and we need to use two of them. And the two we use is when we know three of the things and we've only got one unknown. So I'm not going to use this one because I don't know small b. So I'm going to use this along with this. And what do I mean by use it? So what I'm going to now put in is my sizes. A is the one I'm trying to find, and angle A is 62, and C is 8, and angle C is 54. Now hopefully you'll remember there's a wee technique called cross multiplying, and what that means, we can do A times sine 54. It's a wee bit like the working similarity. A sine 54 equals 8 sine 62. So what does A equal? It equals 8 sine 62 divided by the sine of 54. Calculator time. I do all of that. So we've got 8 times the sine of 62. Now you can press equals if you want, and we're going to divide by the sine of 54 equals, and it's the length of a side, one decimal place is going to be fine here, so 8.7. A is equal to 8 always just go back to your diagram and say, does that seem right in the right scale of things? Remember, one thing is true about triangles. This is the side we've just worked out as 8.7. Bigger angle, we would expect it to be a slightly bigger side compared to this one. Smaller angle, smaller side. Okay, so I would expect it to be bigger than 8. So if I'd got an answer of 5 point something or other, I would know I'd done something wrong. Okay, so that's an example of trying to work out the length of a side using the sine rule. Okay, here's a second example. Look what we're looking for this time. Angle XYZ. There is there. We're trying to find the size of that angle. So the sine rule works for angles as well as sides. So this time we're going to set it down like this. So again, we're going to say using sine rule. And we're going to make it relevant to this particular triangle. So we're in terms of x, y's and z's. So x over sine x is equal to y over sine y is equal to z over sine z. Now, don't get pulled because it's an angle this time. We do exactly the same as we did before. We tick off the ones we know and the ones we're trying to find and so on. So I'm trying to find the angle at y. So I'm trying to find that. So I need to be using this ratio. Let's go through the rest of it. What is 15? That's small x. So I know that one. Do I know the angle at x? Yes, it's 70. Do I know small y? Yes, it's 12. Do I know angle z or small z? No, I don't know that, or I don't know that. So the two ratios I'm going to use this time are those two. 3 things I know and 1 thing I don't know. That has to be the case. So now when I use these two ratios, plug in your values. X is 15. Oh, I just change my colour here. So x is 15 and the angle at vertex x is 70 equals y is 12 and the one we're trying to find is sine y. Okay. Remember technique again, cross multiplying, and what we're going to put on the left hand side of the equation, well, we're going to put our unknown, so I'm going to do the 15 sine y first. So 15 sine y equals 12 sine 70, and then take the 15 over, so I've got 6 sine y equals 12 sine 70 divided by 15. Now I've got one extra line of working in these types, but let's work that out first. So sine y equal to something, get rid of that. So we've got 12 times sine 70 equals divided by 15, which is that horrible thing. 0.7517, 0.7517, right? But again, just as we did it in the earlier lesson on the area triangle, I'm now going to hit my shift key and my sine key. So I'm going to look for inverse sine or second function sine. Why? Because that will get us the angle. So I've still got this value 0.7517, so I'm just going to leave that there. So shift sine of that answer equals, and 1 decimal place will do fine for the angle, 48.7 degrees. Okay, and therefore that angle there, Q angle, 48.7 degrees. So sine rule to work out either the length of a side or the size of an angle. And basically now you can go on and have a look at the work in the pack or your textbook. Okay.